Today on Gabeland, hi guys, and today on Gabeland, I'm going to talk to you and have fun about topology. I'm going to give you a brief intro about topology. Topology is basically how different shapes can morph into each other, and how shapes and there are certain categories of shapes generally made by the number of holes, because you can't close up or open up any, and which means that the number of holes has to stay fixed when you're morphing a shape into one another. So I'm going to show you some of these shapes I've been looking at. Another name for them is manifolds, and there are a few, and there's just a lot of them, but a few examples are like a torus, a cylinder, a Mobius strip, so on. So now, here are the 6 that I've been particularly interested in. So this is just a disc. I know it's not shaped like a disc, but in topology, I said you can morph one thing into another. So now, I'm gonna have to introduce some new notation. So cylinder is, I'm gonna again make a square, but you have to attach these two ends, right? So I'm gonna put these 2 arrows here. The direction will become very important. Now here I'm gonna do a Mobius strip. Mobius strip that's Mobius, and now let me see. So these 2 do have to be connected, but you have to twist one to get it to be a Mobius strip. For a torus, you have to connect each end. So you have to connect those without twisting, but you also have to connect the other ends. So we use double arrows to not confuse them with the other single arrows. So now that we've done 4 of these shapes, the other 2, the remaining 2, I said I had 6 of them, are 2 that are Klein bottle, which is basically a torus with one set flipped, and if you flip both sets, you get a projective plane, which is, so these 2 switch, these 2 are switched. Okay, so now that you've seen all the topological maps, it's likely some people don't know what these 3 are. So a Mobius strip is like basically a strip that only has one side. It's like, I'm gonna try to draw one here. No, that's not good. Okay, so I tried to draw a Mobius strip, and with no luck, so I think it would be better to show you with a piece of paper. I have a strip of paper here, and now this would become a ring, right? So instead, to make a Mobius strip, I'm gonna twist one end so that they come together like this. So now look, I'm going to follow the edge. you know how a ring has two edges? Now I'm gonna try to follow this edge. Oop, I'm back where I started, but on the other side. Now I'm gonna go back. Whoa, it's actually so cool. A Mobius strip has only one edge. So now that I've shown you a Mobius strip, I have to show you the other two or three because not many people know what a torus is. So the torus I'm gonna explain. Yeah, we explained this one. So now the torus, it's basically just like a donut shape, like a surface with one hole in it. If you go out one side, you come back on the other. I'm trying to draw a path there, so I'm gonna erase this. So that's basically what a torus is. Now the other two are a little harder because these two you actually need four-dimensional space to assemble. So I'm gonna have to draw them for you. This a Klein bottle is like basically is get that train. Try and draw one. There, so it's a start. It only has one side. So like I'm gonna go on the side. So I'm gonna go down here, pop through this hole. Wait, what? There, I'm gonna pop through this hole. What? I'm gonna pop through the hole. And I'm on the outside. I'm gonna pop through that hole around here into here, and now I'm on the inside. There is no inside or outside. It's only one side. And so a Klein bottle is basically a three-dimensional Mobius strip because a Mobius strip is just a two-dimensional strip. But try to assemble it in 2D and it'll have to pass through itself. Same with a Klein bottle. It has to pass through itself if you want it in 3D. And so, the final one is the projective plane. I literally don't know what it looks like exactly, but this is the picture that I've seen. No, that's way too big. That's way too big. That's a hole, by the way, and you just have to sneak it in there. That's the pictures I've seen. It's like literally, this passes here and this goes here, I think. It's like a big mess over there. So that's what I think a projective plane looks like, but I can't guarantee it. So now I'm going to talk to you about the Euler characteristic, or as some people call it, Euler number of a surface. So I'm going to demonstrate with a cube. So here is our cube. And so the Euler characteristic or number of any surface is vertices plus faces minus edges. Which means we take, for a cube, we take 12 vertices, no, not 12 vertices, there's 12 edges. I keep saying 8 vertices plus 6 faces minus 12 edges is 2. Now what about a tetrahedron? So again, V plus F minus E. That's vertices 4 plus F plus faces 4 minus edges 6, 2. What's up with all the 2s? So I'll tell you that for any convex polyhedron and a sphere, it's equal to 2. So I'm going to show you some shapes or manifolds that don't have an Euler characteristic of 2. So here are some of the possible values: 2, 1, 0, and -2. So 2 we already covered. I'm gonna wait, and it's just no holes. I'm not writing very well. So so for 1, a projective plane is 1. Now 0, there's quite a lot of them actually. There's a torus with 1 hole. And a Moby strip and a Klein bottle. I keep messing up the spelling here. A Moby strip and a Klein bottle. Now for -2 is a 2-hole torus. I'm going to show you how I got some of these. So I'll start with the Mobius strip because it's one of the simplest. So you know how I showed you with this strip of paper? So now, look. So now it only has one edge. And it only has one face. So we get no vertices plus 1 face minus 1 edge is 0 for the Mobius strip. Now the torus. We can approximate the torus as this cube with a hole punched out with this hole punched out of it, and then these connecting it. That means it has 16 vertices, 16 faces, and 32 edges is 0. So I did the Mobius strip and the torus. I don't think it can verify that a 2-hole torus is -2, but I think other people have, and so if it is, I think I found a pattern for toruses. So now if a torus has n holes, then the Euler characteristic will be 2 minus 2n. That fits with this. So 2 minus 2 times 0 is 2. 2 minus 2 times 1 is 0. 2 minus 2 times 2 is -2. Goes down the line. Okay, that's what I had to talk about topology with you, but and thanks for watching. If you have any questions or suggestions for topics, please tell me in the comments, and I'll try to read them all. Please subscribe and please subscribe if you want to see more videos. And I'll see you next time on Gabeland. Bye.